Good morning. So, my name is Christophe DANO. I would like to give you a talk about the weaknesses in geotechnical structures like dikes or gravity dams made of earth or rockfills. So the outline of my presentation will be the following. First, I will define what is a rockfill. Then I will give you a brief history of dikes and rockfill dams and the engineering implications of that. Then I will show you some results about the geotechnical behavior of rockfills. So I will show you some results obtained in my previous institution in Nantes and now in Grenoble at the 3SR laboratory. And depending on time, I will show you very quickly. I will say some words about another weakness of dikes, which is erosion. So what is a rockfill? Probably you know, but so it's a granular material made of independent rock particles. So it means that there is no cohesion between the grains, and the behavior is purely frictional. The grain size distribution ranges from some millimeters, like a sand, to 1 to 2 meters in rockfill dams. And these rockfills are usually placed in dense conditions. Why? Because the denser, the more resistant and the less compressible. So rockfills can be found in railways. So a ballast is a uniform rockfill. In CFRD, so CFRD are concrete-faced rockfill dam, and also in coastal dikes or fluvial dikes here. So, some words about the history of dikes and dams. So the history can be divided in 4 periods. The first one ranges from ancient times to the Middle Age. The constructions of these small dams, so the construction was done for agricultural reasons, to mitigate flooding and also for water resources. As I said, they are small in height, less than 25 meters, but longitudinally they are massive. So we can find now some existing, so some of these very old dams are still existing. It means that they were well designed and well constructed. And from an engineering point of view, it means that the designer understood that there are 2 main requirements. The first one is the stability of the dam, and the second, and probably the most important, is the water tightness. So from a practical point of view, the well-designed dams are, as illustrated in this picture, the dams are made of 2 parts. The central part is made with clay or a very impermeable soil to ensure the water tightness. And on both sides, you can find rockfills that ensure the stability. Then the second period of constructions corresponds to the Industrial Revolution, so in the 19th century and after. And this period was marked by technical improvements. So a new material appears, concrete, and also a new technology. So some dams constructed in this period use this arch technology And the consequence is that the dams so have a small section compared to the old dams. The third period is the period after the Second World War, where we need very many industrial developments. So this period is marked by higher and higher structures, more than 200 meters high. The objectives were also slightly different, is for irrigation, and mainly energy production, so electricity. From a geographical point of view, this period, so the dams were mainly constructed in Europe and North America, Mexico and the United States of America. And from an historic point of view, this period was also marked by two catastrophic events on concrete arch dams. The first one in Malpasset, France, in 1959. The problem was the quality of the abutment. So the abutment is the lateral side of the dam. Why? Because the geotechnical investigations was not enough, and engineers didn't detect some cracks in the rock. And the second one is the Vaillon Dam in Italy. This dam is still existing. It was not damaged at that time. What happened? So there was a landslide occurred. So in the reservoir, this created a huge wave of water that passed over the crest without any damage to the concrete dam. But the problem was that there was a city at the bottom of the dam, and the city was completely destroyed. And the fourth period, this is this actual period from the year 2000. This period corresponds to the use of a new technology, so the CFRD, concrete face rockfill dam, with very high dams. Most of them were 200 meters high, and the region of interest now are South America, Africa, and Asia. So the principle of concrete face rockfill dam is very simple. You have a huge mass of rockfill to ensure the stability, and a thin concrete face here to ensure the water tightness. Okay? And this type of dams appear in 2000, and it corresponds to the genesis of the sustainable development concept. And the consequence in dam engineering was the use of local resources in terms of human resources, but also in terms of material. I mean that in this type of dams, the rocks was extracted directly in the site. What I don't say is that at the base of the rockfill, you have particles of 1 to 2 meters. So it's quite impossible to characterize this block. And this is a very huge problem, as I will show you later. So before showing some research, I will show you some accidents on this type of concrete face rockfill dams. So the first case is a Campos Novos dam constructed in Brazil between 2000 and 2005. This dam was constructed to produce electricity. Its height is 202 meters. So this is the picture now. But before starting the production of electricity, there was a failure of the concrete face in 2005 during the filling of the reservoir. 6 Olympic swimming pools of water passed through the dam. Okay, so you see the cracks here and mainly here. So the concrete face was repaired, and the dam is now in function. A second very interesting accident happened in Lesotho, so close to South Africa, in 2006. This is a case study of the Mohale Dam with a height of 145 meters. Again, the failure of the concrete face occurred during the filling of the reservoir and after heavy rains. So it suggested that water has an influence. Okay? And here the leakage was 600 liters per second through the rockfill. In the next slide, I list some accidents on this type on the CFRD dams between 2000 and 2010. And what is remarkable is that the cause is, for most of them, is related to the rockfill deformability. Yes, this is the case for the Campos Novos, for Mohale here, and some other dams. So, when accidents occurred, what are the similarities? The period. All of them involved concrete face rockfill dam, so with a huge mass of rockfills. Failure occurs during the filling, what we call the impoundment of the reservoir. There are no problems in the rockfill, but the failure occurs in the concrete face. And what is problematic is the use of local resources because it's impossible to characterize the behavior of the large grains. Okay? So because there are no technical capacity to evaluate the rockfill quality, the height, so more than 200 meters, induce high mechanical stresses at the base of the rockfill. There is a lack of geotechnical knowledge. So you must know that geotechnics is a very, very young topic, more or less 100 years. And basically, there is an influence of the water on the rockfill. So I will try to explain why there is an interaction between the water and the rockfill. So it means that there is a mechanical issue, but also I write hydro, but it's mainly an interaction, a chemical interaction between the water and the rock. So the first question is the behavior of a small particle similar to the behavior of a large one? So to evaluate this effect, what we call a size effect, we perform a very, very simple test. We put a grain between two plates. So this is a Proto-Diakonov test from the Russian school, but we can do the same with only tip So this is called the Franklin test from the American school. So we decided to perform proto-Diakonov test. So we put a grain between two plates and we compress. And we note the maximum force, and we compute the failure stress, sigma f, by dividing this force by the square of the average diameter. And what we observe is that the failure stress is decreasing with the size of the particles. So it means that there is a large scale effect. The largest it's more easy to crush or to break a large grain than a small one. Okay? So yes, there is a scale effect at the grain scale. So we have some statistics. We can fit the data with a variable distribution, and we can implement this law in some numerical computation or numerical code. Second question is, do we have the same effect at the sample scale? So to do that, we perform some triaxial tests. So a triaxial test, it's a common test in a geotechnical lab. So a triaxial test consists in preparing a soil specimen. Then we apply an isotropic compression using water around the specimen. And then we shear the specimen by applying a vertical force. So we use a standard cell. So the specimen here is 100 millimeter in diameter. In this standard cell, we prepared a soil specimen following this grain size distribution. So the maximum grain size is 10 millimeter. So it is more or less a sand. So to give you an order of an idea, it represents about 1 kilogram of soil. Then we test a second grain size distribution here in blue with a maximum grain size of 40 millimeters. But we have to respect a condition of representativity. So in geotechnics, we have to the sample size must be at least 6 to 10 times the maximum grain size. So if we experiment a soil with a maximum grain size of 40 millimeters, we have to increase also the size of the specimen. So we use a second cell here with the diameter of the specimen is 250 millimeters. So we have such a cell here in Grenoble. So again, to give you an idea, it represents more or less 40 to 50 kilograms, at least 2 days of test. And then we test also the third grain size distributions with particles up to 160 millimeters. And then we carried out tests on the largest triaxial cell in Europe with a sample diameter of 1 meter. So here the mass of particles is more than 2 tons, 2,000 kilograms. And a test takes 2 to 3 weeks. Okay? So I will show you some results from this experimental campaign. And now the challenge is to elaborate methodology to upscale or to extrapolate these results with a maximum grain size of more or less 200 millimeters to the field conditions where particles can reach more than 1 meter. So this is the challenge now. So what is important first is to observe this curve. When you compare, so I just put the results from the intermediate cell and the largest one so the intermediate in blue and the largest cell in red. And an indicator of the strength of the resistance is what we call the friction angle from the Moore-Coulomb failure criterion. And when we compute the friction angle obtained for different confining pressure, we observe that the friction angle is decreasing with the confining pressure, but also with the grain size. So it means that the largest grains exhibit less shear strength than smaller grains. So this is very important when you design a very, very huge CFRD. You have to extrapolate and to take some safety of factors to take into account this phenomenon. So what is the cause of the decrease of the friction angle? In fact, we observe that it is correlated with the breakage of the particles. And as I said before, the largest particles are more prone to failure than the smaller one. And this is exactly what we observed. So, as a summary, we have a decrease of the shear strength when we increase the particle size because of the breakage of the particles. And another thing is that we have a more compressible volumetric behavior. So it means that the volume of the rockfill is decreasing more easily. So in terms of dam and engineering, it means that the rockfill will suffer from settlement. Okay, some observations from the field to introduce the interaction between the rockfill and the water. What we observed when you monitor a dam is that the settlement of a dam is increasing with time. So it means a settlement at the crest of about 1 to 2 meters for a dam of 200 meters high. So it's not negligible at all. And when we correlate the rainfall with the settlement, you see that there is a strong correlation between both. So yes, there is an interaction between water from the rainfall or from the reservoir and the behavior of the rockfill. So to study that, we perform some 1D compression test. So we put some grains into a box with no lateral deformation, and we apply a vertical stress on it. And we compute the void ratio. So the void ratio is just a measurement of the volume. So when the void ratio is decreasing, it means that the volume of the rockfill is decreasing versus the vertical stress here. In a log, no, it's not in a linear scale here. In black, you have the compressibility of the rockfill in dry conditions. In blue, the same, but for the saturated condition. So the behavior is quite different. And then what we did, we prepare specimens in dry condition, and at a certain point, we fluid the specimen. And what happens? So dry here, then we add water to saturate the specimen, and we noted a sudden collapse of the rockfill. And at the end, the volume of the rockfill match with the volume of the saturated soil. So these tests were done on a calcareous sand. Okay? And if we do the same with glass beads, we are insensitive to grain crushing. There is no effect of the water. So this effect, the sudden collapse of the specimen, is due to the interaction between the water and the particle because of breakage. Is this only an instantaneous effect? The answer is no. So here you have the evolution of the volume, again in a 1D compression test, during four months. And we had also data over a period of 2 years. And this is exactly the same. So here, the compressibility of the specimen in dry condition. So you see that there is a gradual decrease in the volume. And this decrease is more important in the saturated conditions. So what we observed in the lab corresponds exactly to what was monitored in the field. So the problem is this long-term effect due to the water, to the interaction between the water and the rockfill. So now, how can we explain the failure of the Campos-Novos dam? So as I said, the failure occurs during the filling of the reservoir. So even if the concrete phase is assumed impermeable, there's still some water that passes through this concrete phase or around. So some water touch the large block at the base. There is a chemical action between the water and the rock blocks, so inducing a breakage at the base of the dam. The breakage induces a volumetric decrease of the rockfill, so there is a settlement of the rockfill mass. And because the concrete face is stiffer than the rockfill, the concrete face will suffer from bending, inducing traction in the concrete. And traction in the concrete means failure. And this is the mechanisms here that explains the failure of the face and the leakage. Another weakness of dams and dikes is erosion. So there are at least two types of erosion. What we call the external erosion. So the water goes over the crest, and because of its energy, will detach particles downstream, and gradually we have a loss of stability that could lead to the failure of the dike, or the internal erosion process. So in France, we have many problems of this type. So the first assumption is that we have an hydraulic gradient between the two faces of the dike or of the dams because of the difference of the water level upstream and downstream. So an hydraulic gradient means a flow of water inside the dam. And if the flow is fast enough, it can detach some small particles inside, creating voids, so a local change in porosity, and it can continue over time. And at the end, you can have a tunnel inside the dam and a leakage, as you can see here. And sometimes it also leads to a failure. This is what happens during the Katrina storm in the United States in 2006. I don't remember, 6 or 8, I don't remember. So in that case, we have a change of the mechanical properties, mainly the porosity, and the hydraulic properties, because we have a change in the permeability, and then can lead to the failure. So as a conclusion, still now the rockfill behavior is not completely known. We have again to work about the upscaling of the behavior to fit with the field conditions. Okay, the sustainable development is a good thing, but sometimes have some shortcomings. The fact that we have to use local rock resources means that the mechanical properties are not necessarily optimized. The rockfills are very sensitive to stresses and water, imbibition or flow. And the problem is that we have to monitor, it's a very important requirement to monitor these very, very huge dams to follow the evolution of these structures with time. Not only the settlement, but also the flow of water inside. Thank you for your attention.